Hello everyone. The title of my talk is Why You Shouldn't Stand on a Topological Insulator to Change a Light Bulb. Uh, Earlier in the day, Ranjini was telling you about how clay is neither a solid or a liquid. So here I'll be telling you that a topological insulator is neither a conductor nor a insulator. So that will be part of what I'm telling. But since I'm going to be taking advantage of the fact that I'm the senior most, other than Rajaram, of course, person over here to also give you people some advice. And also, I'll be talking a little bit about gender in physics, because that's also something I've been working on. So I'll start with that. And then in the end, I'll talk about this subject. And this I'll give more at a public lecture level with lots of pictures. Hopefully, it will be less mystifying, because some of the students were saying one of the things that they found very difficult to understand is how does an electron fractionalize? What do you mean by a fractional electron? So I'll do that. So to start with my basic background, I grew up in Hyderabad and Baroda, which is now Vadodara. And I finished high school in Vadodara in a girls' high school. And I was always interested in puzzles, detective stories, and those kinds of things. Academically good. But in my school in Calcutta, it may be very common to take physics if you're a good student. But in Gujarat, it was not. And I was wondering, everybody took medicine and engineering, so I was wondering whether I should take science. I had a supportive family, as Mahua was saying. In our generation, fortunately, most of those who came up did have supportive families. And so we grew up with books, even though we were not particularly well off for something. But I took something called the National Science Talent Scholarship exam and got selected. So that gave me the boom to take physics. And when I see all of you people over here, it reminds me of the science talent summer schools that we used to attend. Only thing is that the ratio was a little different there. There was 40 boys and 8 girls. And I can also, this I'm addressing to people who come from maybe one girl from somewhere and who may be feeling very diffident, homesick, cannot talk, feel everybody else knows a lot more. I was one of those kids. I went home after 2 weeks because I felt I couldn't understand anything. So I just want to tell you, if you feel that way, and I later regretted that I didn't take advantage of it. Many other opportunities which I didn't take advantage of. But don't worry, life will always give you second chances and so on. You try your best. Maybe this time you didn't do. There'll be other summer schools you'll attend. There'll be other schools you'll attend. And you'll do much better. Each thing, as yesterday Pallavi was also saying, don't worry about your failures. They'll help you, right? So it happened to all of us. It will happen to some of you as well. Some of you maybe are already confident, but some of you may not. So I'm addressing those people. I got my bachelor's degree in MS University in Baroda, then master's degree in IIT Bombay, where also I had first got 5-year MS program. I did not go and because I was scared in my case. But for many other people, it could be because they don't have money, their parents don't send them. Many cases I know that their parents would not send them, even if they got admission. So don't worry about it. Life will give you second chances. If you can't go for your bachelor's, you'll go for your master's. If you can't go for your master's, you'll go for a PhD. So this is what I wanted to say to encourage. Then after that, I got more confident. I went for a PhD to Stony Brook University in US. And my PhD was in particle physics. I worked on something called neutron anti-neutron oscillations and B-L violation in grand unified theories. So what are grand unified theories? All of you know that Maxwell unified electricity and magnetism in 1865. And you may not have heard this theory, but in 1967, there's something which those of you who are interested in particle physics may have read at some popular level. There's something called an electroweak theory, for which you might have read things, for which they got the Nobel Prize in 1979. So when I went abroad for a PhD, the idea was that maybe you would also have strong interactions, weak interactions, electromagnetic interactions, all of them unified in the theory. At that time, people were not thinking of unifying gravity. Later, gravity came, which is what led to string theory. But at the time I was doing a PhD, there was no string theory. So this was something else I wanted to say, which Pallavi also mentioned. Marriage is a problem for everybody. And I got married to Ashok, who also got his PhD in 1982 in QCD, which was a theory of strong interactions, and moved to Fermilab. I also got a postdoc in Fermilab and went there. And this is something which is a problem even now in many places in India as well. If you're married, they will not give you positions together, I gather. Even today, that has been happening. At that time in US, I don't know what the story was, but anyway, they didn't know before we went that we were married. So I got the postdoc and I went there. But now I think in US, there's affirmative action, so they will try to get couples together. In India, that is still not the story. In many of the IITs, IISERs, I have heard stories even today that people discourage couples, which is a ridiculous thing. And the gender working group does try to change all these things. But I mean, the number of women at levels where we can change it are still very small. We need far more women to be able to change some of these outdated laws. So in Fermilab, this is another point I wanted to make. I worked on the phenomenology of particle physics, but I also worked on something called topological field theories in 2+1 dimensions. This actually turned out to play an extremely important role in my later career as a condensed matter physicist. At that time, we were working on it from the high energy point of view, just as a topological field theory, not with any applications to condensed matter physics. And today I continue to work on topological quantum matter. So we came back to India in Bhubaneswar. I came back to Institute of Physics in Bhubaneswar after a second postdoc. And Ashok went after a second postdoc at Stanford to TIFR. And we had about 10 years of commuting marriage, but I was in Bhubaneswar and he was in TIFR. And it was we used to travel by train those days because flights were not so common and also very expensive. But fortunately, I was lucky again. This is something which doesn't happen to everyone. And anyway, you have to be very strong. You have to not listen to what others say. If you want to do it, you do it. If you want to stay apart, you do it. Even now, one of my students and his wife have been staying apart for 10, 15 years. And because both of them want to do physics. So one is in Delhi, one is in Calcutta. So you have to do that. But sometimes you don't have a choice. For us, it was lucky that a new institute opened in Allahabad with Professor Mani, and both Ashok and I got positions there. And from 1995 till 2021, that's where we worked. So my entire career has been in Allahabad. It was a new institute, so we were the beginning faculty. That was a good experience for us. So my research interests changed over the years, and I switched in mid-90s to condensed matter physics in order to carve out my own territory. I'll say more about that later. It was initially hard since my contacts abroad were mainly in particle physics because I'd done my PhD, my advisor and all were in particle physics. But there's something called ICTP in Italy, which is similar to the ICTS. ICTS has been based on ICTP, where they would have summer schools in various new subjects for not just students, but also for young faculty from the third world. Essentially, it was a third world institute where people would come have summer schools. Sometimes there would be people from the first world also would come there, give lectures. Some of the third world people would also give lectures. And the main point for us at that time was it was fully paid for. So because this was in the 90s, there was not much travel money in India, so people couldn't go abroad very easily. Now there is a lot more money for travel and so on. But I don't know, by the time you people come, I think the story will be similar, because given the fact that they're cutting you money into sciences. Internet and email also came later. So these trips were really important to keep connected, because science, as you have figured out from now, is a global activity. You have to know what the rest of the world is also doing. You can't do it in isolation. So I got interested in spin systems, and in collaboration with Deeptiman, who was also for switching from HEP to condensed matter for his own reasons, He wrote many papers and worked out a non-linear field theory for a well-known model called the Majumdar-Ghosh model. And that's when I also got interested in fractional quantum Hall effect, initially because the person who wrote it was a couple of years junior to me in Stony Brook. So I was curious and I just picked up the paper and started reading it, but then found that it's very well written and I got very interested in the field. So my lifelong affair with anyons, which is my current interest as well, started from then in the 90s. So I wrote something called the Anion Primer, which is kind of an easy book to start with for anyons. And many students claim that they use it till today. So over the years, we worked on Luttinger liquids, and we got an interesting result. Like you people would have known now about Ohm's law and so on, right? But if you have very, very narrow wires and you have these junctions of wires, what you find is you can't just use Ohm's law. You actually have to find out what exactly happens at a microscopic level to understand these nanowires. And it's a theoretical thing that we wrote, but later people started making these nanotubes, and then some of these things become relevant. Worked on graphene as well and quantum Hall in graphene. But the last 10, 12 years, I've worked on topological quantum matter, and that's what I'll tell you in the second half of my talk about, a little bit about it. And Majorana modes, which actually Rekha also mentioned, is a special kind of anion, an abelian. So now I also wanted to tell you people about these gender-based struggles that all women, at least in our time, and what makes me sometimes sad is that it continues to be the same even 30, 40 years down the line. That there is some kind of struggles that people have to go through to do well in physics. In my own family, I came from a family where I was encouraged because my mother had not been. When she wanted to study, and even her principal came and told my grandfather, he said, no, she's a girl, she cannot study any further. So because of that, she wanted me and my sister to study as much as we wanted. So we didn't feel any gender discrimination at home. Me and my brothers were treated the same. But that's not, again, particularly after going to Allahabad, I realized that how privileged we were, because it's not true in most families, at least in Allahabad and Kanpur and places like that. I didn't feel gender discrimination in my bachelor's in MSU, and even in IIT, we were a very lucky batch. We had 8 girls and 8 boys. That is the first and only time it's been like that. It's almost never that way. And our class was also exceptional. By and large, the girls outperformed the boys. So they would come to this thing for problem solving and so on to our hostel. And we didn't have the problem that there were enough people in our hostel to discuss. In retrospect, there was a lot of sexism and gender bias in IIT. Professors would ask us kind of patronizingly when we wanted to apply about, do you think your parents will send you? Should I waste my time writing a reco for you and all that? But it didn't bother us. We didn't pay attention, and we were happy because there were 8 of us. We could happily do what we wanted. The fact that we were oblivious helped us. So I would say that even when people kind of discriminate, kind of don't pay attention, as Pallavi was also saying yesterday. Just wear blinkers, do what you want. Don't pay attention anyway. I didn't face overt gender bias during my PhD and postdoc years abroad. But when we came back as faculty at IOP and other places I used to visit, then I realized that it was very hard for a young woman physicist, a young faculty member, who was like postdocs, who was pretty young. I was 30 when I came back, 30. So people don't take you seriously. I used to have students saying that if you correct me or scold me, I feel like I'm in kindergarten. I've only been taught by women teachers in kindergarten. So I don't want to listen to you, kind of thing. So there would be a lot of people will say, okay, your seminars, then they will judge you by the way you talk. If you're not very aggressive, that also counts against you. So those kinds of things used to play a role. And I was also married to a star. So people from TIFR, including senior faculty, used to say things like, I mean, why don't you just give up and come to Bombay and get a job in some place nearby? And I used to get so irritated at the time, I remember even saying things like, I'll get divorced. So one of the senior faculty said, because he used to say, you'll anyway be always known as Ashok's wife. So I would say, I'll get divorced. So he said, okay, then you'll be known as his ex-wife. It's a joke now, but at that time it used to really irritate me a lot. So then at some point I decided to switch board because of my scientific interests and otherwise to condensed matter physics. And that was actually, in retrospect, a very good decision because it's also the kind of physics that I like. I like things which I can see and interact with a little more than the purely abstract string theory and things like that. I will also say life improved as I got older and started having PhD students. You people have already met my first PhD student, PK Mohanty. So I'm really grateful to him because he did not have any biases, anything, right? Many of the other students would ask, I told you, you have to ask your senior students, but if you have no students, then there are no senior students to ask. So somebody should have enough confidence in you to join you, right? So he was like that. He didn't have any biases. He just joined me. And after that, my life improved a lot. So regarding my involvement in women's issues, I started thinking about these issues in the early 2000s when I was asked from an international body called International Union of Pure and Applied Physics to collate a questionnaire regarding women in physics and present it to an international working group. They couldn't get this data easily from India because we didn't have any data on women in physics at that time. So I actually sent it out to people whom I knew, so about 30 people and so on. They asked for 30, so I initially gave it to 30 people. And at that time, most women, including me, said that there was no bias. We had all faced different kinds of discrimination, but everybody thought it's their personal problem. I thought it was I had some issues, somebody thought they had other issues and so on. But it was then we we had these IUPAP conferences in women in physics, which even goes on now every 3 years, 2002, 2005 and all, which brings together women from all countries. In the first one, there were 5 people from India, 5 people from every country. And then they had working groups made over there. Then they discussed what is common between the different countries, what is different between the different countries. And we compared data. And India was doing better than many other countries because girls were not discouraged from doing physics in schools. In places like US or even more so the Northern European countries, even at school level, people were discouraged. And there were very few girls taking science in schools. In India, the major problems started later at PhD and postdoc levels because of family problems, marriages, etc. And also, this is something I came to know as I lived in Allahabad. There's a lot of difference. India has, of course, many countries, as many of you know, many countries in one. So in some parts, we may look like we're like a developed country. In other parts, we look like a completely underdeveloped country. So things are very highly family dependent and depends on which part of a country you come from. So in Allahabad, there are schools where they say girls should not do physics. Girls should not do science. Right? That isn't something I'd seen earlier, but I saw it in Allahabad. But in India, now the main things have changed over the years. And the main problem in India, as far as we can see, is that faculty positions are scarce. And there's always a two-body problem where the women and men are in different places. And usually it is expected that the woman is the one who gives up and goes and stays where her husband stays. So I will say that things have improved. If you ask someone like me, in the last 30, 40 years, things have improved. And the young women today are much more aware of sexism. There are more positions, and the number of young faculty that I see when we have these various young faculty meetings, there are many more women that we see. But I mean, these things, some of these things I'll hear from them that even now they feel they're discriminated against and people do not give them the same kind of respect that their male colleagues get. The current status is that we now have a gender in physics working group called GIPWG, which was formed by the Indian Physics Association in 2017. This also has subject working groups like condensed matter physics, high energy physics, nuclear and accelerator physics. The astrophysics actually has been a little more advanced and they have started even earlier. I think since 2015, they have gender working group in physics, which I think Sushan was the first chair. So this group has helped a lot. They've initiated lecture series by women physicists, and they work towards equity and inclusion in science and technology, not just gender, also LGBTQ and other underrepresented groups are also taken care of here. And there are many other initiatives, including this SSWP here, started 3 years ago. Vigyan Vidushi started, I think, around 2020, etc. So now, before I start my work, I'll just say that how do I look back on my years, because I'm now retiring as a physicist. It's been fun. I worked in many fields with many collaborators. And in recent years, I've got some recognition and I've become some fellows and so on. I've been also the divisional associate editor for PRL. And main thing is, but my major contribution to my field, I would say, has been my students. I've had many PhD students, many more master's students and visiting students, and I've actually loved mentoring all of them. And actually, I have learned as much or more from them than I've taught them. Many of them are now faculty members at IITs and IISERs, so they have students whom I call my grand students. So we have pictures of, I should have put it, I have a picture of me, Mohanty, PK Mohanty, his first student, and her student. So there's 4 generations in a picture. Huh? Udna Basu. So with this, I'll come to this subject. The second half of my talk will be about, is there any question, or maybe I should take questions after the second part of the talk. So this is this thing of why you shouldn't stand on a topological insulator to change a light bulb. And first word here, which is difficult, is topology. Topology is a branch of mathematics dealing with shapes. So let me just give a demonstration. If I have something, I'll have something like this, right? Unless you cut it, you can't make it a straight line. Now I can also take this like this. It's the same loop, this thing, but now the point is it's looped, right? And the loop can be moved from my hand to this. It can move any way you want, right? But what you can't do is make this go back to the original round shape without leaving this, right? This is because it's something which belongs to the entire system. You can't, the only way is to cut the wire. You only cut the wire and then you can go. So this is what I've been over here by these various, from here, if you want to go here, you have to cut the wire. Similarly, you can have 2 loops. I can't make 2 loops with my hands, but you understand what I mean, and so on, right? Similarly, the surfaces in 2 dimension, to go from here to here, you actually have to punch a hole, right? There's no smooth deformation which will take you from here to here. On the other hand, this one can easily be changed into a donut, and this thing which you may have seen many times, coffee cup and donut, which Rekha also showed you. This is something with 2 loops. And this is another point which you might know about, metals versus insulator. You may be familiar with metals which conduct electricity and insulators like diamond, wood, rubber, which don't, right? Now what a topological material is, there is a material which conducts electricity only on the surface and not on the interior. So it essentially behaves as if it's like a piece of wood with a metal all around it. But it's not two materials, it's one material. It's just that the states on the surface are different from the states inside the surface. So the behavior is like this. And it's not because if you cut it, for instance, it's more like a magnet. Each time you cut it, you'll get new surfaces, but that surface will again conduct, right? So it's not like just cutting a piece of wood with something around it. So it's a very unusual, I don't know whether you'll call it a metal or an insulator, right? It's a metal on the surface, it's an insulator inside. So this is the joke, which is due to R. Shankar from Yale University. So don't stand on a topological insulator to change a light bulb, right? Because it's metallic. It's like standing on a metal to change a light bulb. In case there is any short circuit, you'll get electrocuted, right? So this should have also been this thing. I'm just showing it to say it's a topological insulator. I'm not talking about surface currents will be much less than if the full thing carried current and all that. So we're not worrying about that. This is just a joke. So the first property that you need to know about topological insulators are that the surface states are different from interior or bulk states. And why are these materials different? I mean, as I said, it's not that it's really a metal wood covered by metal. What is the difference between these materials is like essentially the difference between a rope with a knot and without a knot. But this difference, the knot and not opening of a knot, is something which happens in a space called the momentum space. So the quantum mechanical wave functions of the electrons in topological insulators are knotted in momentum space. To understand this, you'll actually have to do the quantum mechanics. You have to learn things about quantum mechanics and see how the wave functions behave under periodic in a Brillouin and so on and all, as she mentioned. But I'm not saying all that. All you have to know is that it's like for topological insulator, the wave functions are different. They're in a different class than when they're non-topological. So that's what's up. Interestingly, such materials were predicted first and discovered soon after. And this is something which is actually very unusual in condensed matter. In fact, Ashok told me in IIT Kanpur, somebody told him that if you want to do condensed matter physics, do experiment, because things are always first discovered experimentally and then you have to explain them. In high energy, on the other hand, they're discovered theoretically first, because you first predict them, then they build these huge accelerators and then they find these things. But this was very surprising that they were predicted first. And they were discovered actually theoretically only in this century. But in the 1980s, it was realized that if you subject normal matter to extreme conditions, very low temperatures and very high magnetic fields, then it was possible to have conducting edges and insulating bulk in a 2D system, which was called the quantum Hall effect. This may not be something familiar to you, but I think many of you know the classical Hall effect, right? Do you know the classical Hall effect? You know the Lorentz force, right? So what you do is that you apply electric field in this direction. You apply current in this direction. So electric field is in one direction. You apply magnetic field perpendicular to the current. And if you have crossed electric and magnetic fields, then you know that there will be a voltage in this direction. Some of you, this is not done in BSc, classical Hall effect. Not the first year. It's just electromagnetic this thing, that you have an electric field going in one direction, magnetic field perpendicular to it. And because of the crossed electric and magnetic fields, the electrons actually drift in the third direction. So there is a field in this direction. There's a magnetic field which is perpendicular to it. And then the electrons actually drift. So that's why there is a voltage drop which is created across in the perpendicular direction. That is what is called the Hall effect. And then if you have this experiment, it was known from many, many years. I mean, ever since electromagnetism was discovered. But then when they did the experiment at very low temperatures and high magnetic fields, they found that the conductance actually forms plateaus. And at particular integer values, and this is something called conduction quantization, which is extremely, extremely accurate. So let me say, I mean, you know about charge quantization, right? You must have heard of Millikan's oil drop experiment. There it's like an electron, you're looking at single electrons sitting on an oil drop, right? So that is the way, by measuring, equating the electric field and the gravitational field and all that, making them stop, you get the charge of the electron. But here what has now happened is that you have a material which has many, many particles. The experiment is done in many different labs. It will have lots of impurities, disorder, etc. But in every case, they're finding exact quantization. So this exact quantization is extremely unusual. Why is this charge quantization so accurate in a many-body system? That's a question that was asked. And today it is so accurate that the RK, which is the h by E squared, it's called the von Klitzing unit. It's considered, it's the minimum resistance that you can have. Minimum E squared by H is the minimum conductance that you can have, rather. And this is considered a fundamental constant of nature. In 1990, this was internationally accepted as the standard for the unit of resistance. So this is very surprising that it is happening in a very complex system. Not normally fundamental constants of nature, you will think it is happening due to one particle, two particles, and something like this. This is in a many particle system. You don't even know how many particles, right? Every lab will have its own. And the reason this happens is because here also the edges are different from the bulk. Only the edges of the quantum Hall sample carry current. And they carry current only in one direction. I can't explain why this is true, but I'm stating it as a fact. You can think of it roughly because of electric field, magnetic field, and the charge will move in one direction. So it's like basically you have one way. Current moves only in one way. Okay? And this is, the analogy is with traffic. If you have one-way traffic, it will move very smoothly. There is no backscattering. Even if it finds an impurity, it will just go around it. It cannot come back. So its quantization remains extremely, extremely accurate. So with this analogy, I'm hoping that you'll get the idea that this is now the integer quantum Hall effect is understood to be the first topological phase, which was there in the 1980s. Because the explanation for these topological insulators, all of these are related to this. And later on, people also found something called the fractional quantum Hall effect, which were discovered when this is what requires fractional electron and so on. But let me try to give an analogy for that. To understand this, you need to understand the concept of fractional charges. And first, I can start with the idea of emergent particles. Why would you even think that it is easy to understand a many-particle system? It's not even easy to understand how single atoms behave. How is it that we actually end up, as PK was saying, that even a three-body problem is difficult, right? So how do we understand finally that when there are so many particles in the system? Statistical mechanics, but here what I'm going to talk about is the miracle of what is called emergence. Many particles sometimes conspire to behave in a simple way. So it's not that when you think of a light bulb, electrons are not going smoothly like this and through little points in a conducting material. But even for the simplest lithium atom, actually you know that the electrons are actually wave functions, right? So they form densities. So that there are two electrons close to the atom, one which is further away. And if you put them in a crystal, you have to solve what happens when an extra electron is added to this mess. Even harder for copper or silver. So what happens is that when you think of adding an electron, it's some kind of a density wave which is going through the material, right? It's like you're adding an electron, but the electrons are all kind of the densities over there, right? Because it's like this, some kind of a mesh. And then you just have to think of them as if this extra, it sometimes happens that even though you've added one, it's this some kind of a increased probability density goes through the material. So the miracle is that you can think of the moving object as an electron. It's not the original electron, but it's something called a quasi-particle or collective excitation. We still call it an electron because it behaves like a particle. It has a mass which could be different from electron mass. It has a spin, it has electric charge. So they behave as if you could describe them as single particles, though they're actually in a big mess, right? As an analogy, you can think of bubbles in a liquid, right? The bubbles can move, if they're long-lived bubbles, they're collective excitation, but they can move and scatter against each other, right? So that's a kind of analogy that one can give. But in 1983, since 83, when the fractional quantum Hall effect was discovered, we've realized that under some conditions, these emergent quasi-particles can also behave as if they have fractional charges. This has nothing to do with the original electron. It's not that that gets fractionalized, but these emergent quasi-particles behave as if they have fractional electrons, fractional charges. And this happens essentially in topological systems. And these fractionally charged quasi-particles are what are called anyons. Right? It's like you're starting with a person and putting them apart. In the fractional quantum Hall effect, you get E by 3 quasi-particles. In the Majorana case, in a semiconductor wire, you can get half quasi-particles which have half a charge of an electron. So the second property that all these topological materials have is that of charge fractionalization. So yeah, as I already said, the first topological systems were the integer quantum Hall effect and fractional quantum Hall effect, but they needed very low temperatures, high magnetic fields. Topological insulators, which were at room temperature and without magnetic field, were only discovered in 2008. And they were in fact predicted first and then discovered. And now, of course, by now, many materials are known. And why did it take so long to discover them? Both theoretically and experimentally, it needed more work. We needed to have experiments which could tell which part of the system is carrying current. That was not so easy earlier before you had the instrumentation. And the final question, why are we interested? The current interest in these materials is because they have many real-life applications. You can have energy-efficient electronics because currents can flow without dissipation. I haven't talked about this. I'll only emphasize one important application here, topological quantum computers. You may have heard of this. I think we would have heard of, at least at the popular level, that there are these qubits, right? Classical bits are 0 and 1, and qubits are linear combinations, right? You can have A times 0 plus B times 1, right? And they're quantum mechanical in nature and can exist in superposition states. So this makes it possible for qubits to store much more information and perform calculations much easier than classical bits. But the problem with qubits, if they have spin, is just that they'll flip very easily. If you have spin up and spin down as your qubit, they can flip very easily by temperature or any disorder. So now what people are thinking of is to make these non-local fermions. Because if I have split a fermion, split in the sense, as I said in the words, it's as if you have E by 2 charge here and E by 2 charge here, and you can think of them as, in some sense, of making a non-local fermion. Then it'll depend on whether this non-local fermion state is filled or not filled. And in that case, what happens is that any disturbance at one end will not affect the occupation of this state, right? So because of that, it will be very stable, very long-lived. And you can have gates which are made by braiding these fractionally charged particles. And this is how we can get topological quantum computers. These are things you might have heard about in the popular press. So I'm not going to go, this is a caricature of what is a quantum computer. You can form a memory from the anyon qubits, you can compute anyon braiding, and then you can measure them. But what is right now, we are at the crossroads where we, at least for some kind of calculation, People have shown that quantum computers can be faster than classical computers for some toy calculations. And at least I believe that in the next 5 to 10 years, it will be solving problems in the labs which maybe cannot be solved by classical computers. Quantum computers are going to be there. Whether it's 5 or 10 years, whether it's 20 years is a matter of opinion, but it's going to come. And when will we be holding quantum computers in our hand? That's hard to say. But I'll end with just this thing. A few months ago, there's something called a Majorana 1 quantum chip, which is released by Microsoft. They claim that this has 8 anyonic quantum bits. The jury is still out. Nobody else has reproduced this. And because they're a company, they have also not given out all the details. So the rest of the scientific community has not yet accepted this. But this is something that you should keep in mind. So to end, let me just say the takeaway points again. The idea of topology is that topological materials are knotted in some internal space. Behavior on the surface of the material is very different from the interior of the material. You can have particle-like excitations, anyons, which are just a fraction of the normal elementary particle, which is an electron. And the current properties of the topological materials are very stable. They're not susceptible to disorder. So, and as a major application, they can lead to fault-tolerant quantum computation. So this is the technology of the future. And I should acknowledge that all the cartoon images were made using ChatGPT, which you've learned about. Okay, thank you. Any questions? Yeah, the quasi-particle is something which is actually what I'm saying is that you have a system which is made up of many particles, and then you think of them as all interacting with one another and making some kind of a mess, right? In general, you can ask is there any easy way to describe them? It turns out in some cases, what happens is that the effective way to describe them is you can think of some new kind of postulate sometimes, a new kind of particle. And in terms of, if you write the theory in terms of those things, you find that it looks as if those are non-interacting. So what is defined as a quasi-particle is the most effective particle in terms of which almost free theory can be written. For instance, in the quantum Hall picture, fractional quantum Hall, this was Jain's big discovery. What he found is that there's composite fermions, which is like as if every electron is carrying 2 flux tubes with it. So part of the magnetic field went into creating this new quasi-particle. You can't ask questions of how it was done and so on, but if you describe your theory in terms of these composite fermions, then it almost behaves like those composite fermions don't interact with each other and can move freely. Yeah. Yeah, there were personal reasons, and okay, one reason was I liked anyons and so on. The personal reason was that my husband was in particle physics, string theory, and then at some point in IOP, there was, at that time, this shouldn't have affected me, but at that time it did. People would say that your husband is helping you write your papers. So I did not like that. It helped to move away from that. Yeah. Somebody else will have to repeat in the front row because my hearing is not that good.
Use a microphone.
Is it on?
Hello.
I did get it.
Ma'am, the electron wave distribution, ma'am.
Wave function, the
yeah,
electron wave function.
You mentioned that those are knotted in momentum space. What exactly is that?
Uh, yeah. So the wave, I mean, you've done quantum mechanics? Okay, normally you have this, there's I think some of you, Schrodinger equation, and there's a wave function, right? And the wave function can be something which is written either in real space or it's Fourier transformed space, which is the momentum space, right? So psi, this psi can be a function of x, or you can also write psi as a function of p, momentum. It's Fourier transform space. And what happens in some of these topological materials is that, and then you also try to, what happens is that there is a certain kind of periodicity in momentum space that comes. That if there is a box of some length L, then the momentum also gets periodically quantized. This is what is quantum mechanics all about. And then what happens is that in that quantized space, right, in the momentum space, just like in real space, I said that something can be knotted or unknotted, right? This can be like this or like this. So similarly, you can see that if the two endpoints are kept fixed, what I was doing is keeping the endpoints fixed. And then you can see whether there's a knot or there's not a knot, right? And similarly, in momentum space also, you can see whether there's a knot or there's no knot. So for topological materials, there is a knot. That's the idea.